Okay, so we had been working on this problem where we had two charges of the same value, the same sign, and we're trying to find the electrical field of the combined electrical field of these charges in 5 points around this two-dimensional space. I had done the first one where the reference point was here in the middle. And the important thing about these problems, and I'm going to be stressing this a lot, to do the free body diagram. Please do the free body diagram. And it's very important in these problems for you to represent the free body diagram and where the electrical fields or electrical forces are pointing. It's very important. And so for this situation, we had opposing electrical fields that in this middle point, since the distances and the charges were the same, the electrical fields were the same, and since it's exactly in the middle and both are going in opposite directions, the resultant electrical field is zero. That's not always going to happen. Depending on where we're located is how the electrical fields are going to interact, and that's what we should have as a takeaway from each of the different situations. So for situation number 2, in situation number 2, the charges, let me just do this. Give me a moment. I should have done this. I'm just going to put the Cartesian, the plane here, just so we know what we're talking about. Give me one moment to update the slides there. Okay. Okay, so yeah. So for situation number 2, now the chart, the point we're referencing is located over here. Okay. And so if it's located over there, we are going to have a resultant electrical field that has to do with the interaction of those two fields. And so if we're located there, we are going to have one electrical field from EA pointing this way. And please, you guys, when you do the free body diagram, which is what you guys did here, please place the electrical fields or forces or whatever we're analyzing, please place them on the free body diagram. So that means that EA is going this way, and then we've got EB because the field is going outwards, and we've got EB going this way as well. Okay, both of them are going to the same side. In this case, each of the situations is going to have a different distance. So for EA, we're going to have this distance from here to here, which is 1, 2, 3, 4, 5, which is 6 meters or units. And for EB, we're going to have this distance here, which is 2. Now, this is important because that means that the electrical fields are going to be different. That makes sense. The further away we are, the lower or the weaker the electrical field is. And that's why we notice that EA is 250 newtons by coulomb. The closer we are, the stronger the electrical field is. So notice that EB is much higher. It's 2,250 newtons coulomb. Now, both of the electrical fields are pointing to the right. So that means that we are going to add them. I remember Estrella asking, how do I know if I'm going to add them or subtract them? Well, simply, we're going to look at where they're pointing, and remembering that the Cartesian plane, if it's on the horizontal axis, the right part is positive, left part is negative. If it's on the vertical axis, upper part is positive, lower part is negative. And so the XY components are going to be added or subtracted depending on where they're facing. Both of these are facing to the right. That means they would be added. And so the result is 2,500. Oh, another thing, you guys, it's very important. Newtons by coulomb. Okay, newtons divided by Coulomb. That's that's important. Okay. Okay. Questions with this one before we move on. Let me update this as well. These to be as exact.
Professor.
Yes, go ahead. Say yeah. Yes, go ahead.
The net force isn't just newtons. I mean,
it's
yeah.
Remember, say it right now. We're not talking about force. We're talking about the electrical field. Okay, so the electrical field again it's this imaginary field that's around charged objects, and the units for an electrical field are newtons divided by Coulomb. Okay, now
Okay.
Estrella, when does this situation, when are there forces involved? It's kind of like the electrical hockey. Whenever I put another charge there, that's where I can generate a force or analyze a force on that charge that's due to the electrical field. So if I were to tell you, I'm going to place a 2 microcoulomb charge in point 2, tell me what is the force that acts according to the other two, then we would use this electrical field and we can talk about forces. But if we're just talking about the effect or combined effect of the electrical fields, we're still working with electrical fields. And the units are newtons divided by Coulomb.
Okay, then it's because I think that in all the problems, we put just newtons. So it's newtons.
This is yours, actually. I copy pasted for yours, and it's Newton's Coulomb. That was just the rest. You did put Newton's Coulomb on it. Just the result, I think, was.
Oh, yes. Okay.
Yeah, in this one.
So
that was a common mistake. I've been noticing that you guys, all of you or some of you are doing that. So just remember, newtons divided by Coulomb. Those are the units for
electrical field.
For electrical fields. Okay.
Okay. Thank you.
Okay. Good. Thank you, Estrella. Okay. Let me just update this here. I'm going to do some real time updating here. In a moment. I just want to update that. Where are we? Here we are. I just want to update it on the PowerPoint so I don't forget to do that later on. Whoops. Almost done, almost done. Be patient. Almost done, almost done. Just wanted to update it in the PowerPoint. Okay, there we go. Okay, that's problem number 2. Now for problem number 3, now we're located on the other side. So we're located on the other side, and on the other side, we've got point number 3, which is located over here. So this is point number 3 here. And in point number 3, we're also going to have two electrical fields. They are also going to be pointing outwards. So both of them are going to be going to the left. Both of them are going to be going to the left. And so we're going to have different distances here as well. Okay. We're going to have a distance of 7 meters for A. Okay. Which is no, I'm sorry, 4 meters. 4 meters for A, and we're gonna have 8 meters for B. And so calculate both of the electrical fields. Obviously, the electrical field in A is larger because it is closer. And so here the difference is that the electrical field, the resulting electrical field that we're going to have here, the difference is that the resulting electrical field that we're going to have here, and let me just also write that down as well. ER is going to be equal to EA minus EB, okay? This isn't going to be equal to 0, by the way, just a quick correction there. It's not going to be equal to 0. I'm just going to rewrite this here on top. The resultant electrical field, so the calculations is correct. I just want to be careful about how we're writing down the nomenclature. ER is going to be equal to, both of the electrical fields are pointing to the left. So it's going to be minus EA minus EB. Sorry. So that means that ER is going to be minus, what is it? 562.5 newtons coulomb minus 703.125 newtons coulomb. That's down up here, so I have a little bit more space. I also want to add it to the PowerPoint. ER, the resultant electrical field, is going to be minus EA minus EB. So the resultant electrical field is going to be minus 562.5 newtons coulomb minus 703.125 newtons coulomb. And that resulting electrical field is going to be, I'm sorry, not minus 703, that's the result. It's minus 652.5 and 140, I'm sorry, 0.625 newtons coulomb. And so the resulting electrical field is going to be minus 703.125 newtons coulomb. And the negative sign there is important because this means that the resultant electrical field is pointing this way. Okay, it's pointing to the left, and it's pointing to the left because that is negative. Okay. Okay. I'm going to update that over here as well in the PowerPoint. Okay. While I do that, questions. Are we okay up to this point? Before we get into the two problems that were a bit more interesting or complicated, which were problems 4 and 5, and at least the teams that turned these in, again, the procedures were correct. The only thing that was missing was the only thing that was a problem there was the was a calculation that, curiously enough, both teams had the same calculation issue. Okay, so I'm going to move on. If there are no questions now, I'm going to move on to the next one. Okay. Sorry about that. Okay, now for the next one, it was problem number, actually it wasn't problem number 5 that had the calculation, it was problem number 4 that had the calculation issue. And so for problem number 4, let me do some quick editing here. Give me a quick moment here. For problem number 4, now the charge is located in another part in space where it's not necessarily aligned with the either with any of the axes. Okay, and so in that sense, we have to consider that that situation. Okay, let me just do something here. Just want to copy the problem so we also have it here. It's gonna be a little bit small, but that'll do. Okay, so for this problem, which is problem number 4, now the charge is located here on the, I'm not sorry, the charge, the situation we're looking at is located here on the bottom. And so what happens there? Basically, we're going to have an electrical field due to A that, since it's pointing outwards, it's going to be going to this side. Okay, it's going to be pointing downwards. If we do the free body diagram, which is the one that we see here on the right. And then we're going to have an electrical field due to B that's going also downwards. Now, this situation in particular creates a certain symmetry. So we're actually going to have a triangle here. We're actually going to have a triangle that's formed here. And in that triangle, this angle here, since it's a right triangle, and the distance, it doesn't look at here, but the distances are the same. So if this distance is the same as this distance, so this angle is going to have to be 45 degrees, which means this angle is 45 degrees. And since there's a symmetry here, that also means that this angle is 45 degrees. And so this takes us over here to this situation here. We've got both electrical fields pointing downwards. And there's an angle there of 45 degrees. So this is where I found it curious how decimals can affect calculations. How if we do the calculation of the triangle here, both A and B in this triangle, both A and B are going to measure 2 meters. And so I'm trying to find C, which is equal to R, which would be the distance to the point. And to do that, we use Pythagoras. So we find that C is the square root of 8, which is 2.82, right? But you know that if I do that calculation, that's a rational number, an irrational number, I'm sorry. And so that's going to be a long decimal. There's going to be a lot of decimals there. And so then we come back over here and do the formula for the electrical field. And so we've got the electrical constant, we got the charge, and then we have the distance, which we're using here. But notice that we're elevating the distance to the square. So actually this value here is equal to 8. But if we elevate 2.82 without using all of the decimals, we're not going to get 8. We're going to get 7 point blah, 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 blah. And if we divide by that, we're going to lose decimals. We're going to lose decimals. Different if we divided by 8. So most of you, when you did this calculation, you got, I think, 1137 point something, or 31 point something, or something like that. Which is that decimal, that situation with the decimals. So we can actually literally just use the 8 because of this. So that was one thing I noticed in the calculations. If we use all of the decimals, we should get 1125. And both of them, both EA and EB, both of them are the same. Okay, both of them are going to be the same because it's the same situation. We have the same. We have the same distances here and here. They're going to be exactly the same. And so that value is 1125 newtons Coulomb. And so now we need to calculate the resultant electrical field. And this resultant electrical field, I forgot that this is an E. It's the resultant electrical field. The resultant electrical field is going to be, we need to calculate the electrical fields in the total electrical fields in X and in Y. So we do that. We calculate the electrical field in X. What is that going to be? It's going to be the component of EA that is in X, which is this one. And that's going to be EA multiplied by the cosine of the angle. Always the cosine of the angle, if it's with regards to X, is going to give me the X component. The sine is going to give me the Y component. And that's going to be positive because it's facing this way. And then we're going to have the same situation for EB. It's going to be EB cosine of the angle, but it's pointing the other way. And so that's why it's negative. The thing here is that both EA and EB have the same values. They have the same values. And so since they have the same values, this calculation, both of these are going to be the same. And so they're going to cancel each other out. And so the electrical field in X is 0. We're not going to have an electrical field. Then we're going to have the electrical field in Y. The electrical field in Y is going to be a similar situation. Now we're going to be looking downwards. And so EA and EB are both going to have a component in Y, and that's going to be the electrical field multiplied by the sine of the angle, and that's going to be pointing downwards. Since both of them are pointing downwards, we're going to have minus EA sine of 45 minus EB sine of 45, okay? And this comes from having the sum of electrical fields in Y is equal to minus EA times the sine of alpha minus EB times the sine of alpha. In that case, we're going to have the same values as well. So both of these are actually going to be the same. But since both of them are pointing downwards, then now we are going to have the same value multiplied by 2, or the double of the value, which is actually going to be 1,590. Okay. Oops. Once we do that, this calculation, we calculate the resultant electrical field. And the thing here with the resultant electrical field is that since the electrical field in X is 0, since the electrical field in X is going to be 0, the resultant electrical field that we're going to have is actually going to be the electrical field in Y, which is the 1,590 newtons divided by Coulomb. If we calculate the angle, since the electrical fields in X are 0, that would give us the inverse tangent of infinite. The tangent of infinite means that it's directly aligned with a vertical axis, which means that it's going directly downward. So both of these are going to combine, and in the end, what we're going to have is an electrical field going downwards here. So it's going to have an angle of minus 90. What I noticed here with you guys, both of the teams that houses that turned this in, is that for some reason you lost some decimals over here because of the 2.82, but somehow, I don't know, your calculators, when you multiplied it by the sine of 45, you multiplied it by a different value, and that's why you got a different value over here. And so again, it wasn't an issue that had to do with procedure. It was more an issue that had to do with an error in calculation. Okay. Okay, let me just put the triangle there, so that's clear. In a moment, I'm going to draw the triangle here so I can add it to the PowerPoint as well. This is A. This is going to be B, and this is going to be C, which is going to be equal to R. Okay. Okay, I'm gonna do some editing over here in the PowerPoint just so I can add this and not lose it. While I do that, any questions with this one? Again, both houses that turned this in had the procedure correct. The procedure was correct. The issue more had to do with the error or the detail there in the calculations. Okay. 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 Any questions up to this point? No. Okay. I'm finishing up the editing here. Before we had all these tools, it was interesting how we didn't. So you wrote everything in the whiteboard. You just erased it, which is kind of interesting. Almost done. Okay, I'm going to clear the screen. Okay, I'm going to clear the screen to see if that looks okay. Okay, there we go. Okay, and I think that's it. So questions with this one? No. Okay. And I have to always give credit to people. So there we go. Okay, questions with this one? No. Okay, let's move on to the last one again, just so we're completely in tune to what we're doing. Here to do a correction here as well. And the Zoom, these Zoom screens are really, I'm sorry, the Zoom toolbars are really annoying. And I know I can remove them, but still that doesn't mean they're not annoying. Really annoying. Okay. Put this here and problem definition. There we go. This looks better. Okay, so let's go with let's go with the last problem or situation here. Okay. So with the last problem from this section. So is it okay if we go long? If you guys need to walk, run, go to the bathroom, take some water, and please go ahead. Okay, for the last situation, we have now that we are located, we're going to be located over here in point number 5. So if we're located in point number 5 is directly aligned with charge A. And so we're going to have an if we do the free body diagram there, which was done here on the right, we're going to have an electrical field going upwards. That is going to be the one from EA. It's going to be directly aligned with the to the charge because it's on the same axis. And then we're going to have an electrical field regarding B that's going to be going something like this over to this side. Okay, and there's going to be an angle here that we need to calculate. Okay, and so this is basically this free body diagram. Very, very well done. The angle here is alpha. And over here, we see that we've got the distances represented. This distance here is 2, and this distance here is 2 as well. That gives us a total distance here of 4, and this distance over here is 3. So we've got everything we need to use the Pythagorean theorem and some trigonometry to find the hypotenuse, which would be R, or the distance for B, R for B, and also to find the angle alpha. So we can do that. Very well done. I think Enya did this one. I really like the very nicely written procedure. And so now we find each of the electrical field magnitudes. For EA, we're going to use 3 meters. We get, I think that's 1,000 newtons coulombs. For EB, we use the 5 meters, which was this one calculated here. We get a much lower electrical field, and that has to do with the distance. And then we're going to have the sum of electrical fields in X, and both of the is that X or is that Y? B? Yeah, the sum of electrical fields in X. The only component that we're going to have in X is EB. Because EA is aligned completely with the y-axis. So it's going to be EB cosine of 36.86, but that's going to the left, so it's going to be negative. And so that is going to be the resultant for X. For Y, we are going to have the component of EA that's directly aligned and going upward, that's positive, and the component of B, which is going to be EB times the sine of alpha, and that's also going to be going upward, so both of them are being added. The resultant, we apply the Pythagoras, and we also find the angle. So it's going to be 1,249.59 newtons coulomb. And the angle is either minus 76.67, or another valid answer is to say that the angle is 103 point something degrees. So it's either the negative angle, which would be the 76, or the positive, which is the complementary angle, which is 103. Either of those is valid. Okay. And this one, we didn't have any calculation issues that were relevant. Okay. So questions with these problems before we wrap up this part. Questions? Are we good? Okay. Okay. So let me just save here. Okay. So what will we be doing next? Oh, I said we were going to do 3 things, but I think we're probably going to do 2 things today. Well, maybe we'll get to do 3 things depending on the time. I want us to start thinking about, well, and this is kind of a summary of the resultant forces that are acting and how they're interacting. Electrical fields, I'm sorry, that are interacting. we're going to start talking about this. Up to this point, we've been talking about point charges. So a point charge, again, is defined as this point in space that has an electrical charge. But we don't care about its geometry. We don't care about anything. It's just a point in space that has no dimensions, that has an electrical charge. And so we're only interested in the charge. And for that situation where we have a point in space that doesn't have geometry or dimensions, we know that the electrical fields are going to radiate outwards, going outwards, or pointing inwards, depending on if it's positive or negative. But what would happen if I had an object that had a certain geometry? And that object with that geometry was charged, then how would the electrical field behave? Well, that's what we're going to be talking about right now. And we're going to be refreshing some integrals. By the way, I remember when I was in school and I saw all these things in dynamics and electricity and magnetism that had to do with integrals. I remember we took a lot of time in solving the integrals and doing that. And I want to do that as well, so you know where the expressions come from. I was watching I was looking maybe for some YouTube videos that I could give you guys where you could see what I'm going to do today, what I'm going to be doing for these examples today and maybe Monday. And I found it funny because I was looking for videos that did the procedure but solved the integral. And I was finding very funny with some of the instructors that were like, well, okay, here is the demonstration and here is the integral. And well, everybody knows that the result of that integral is this. And I'm like, wait a minute, buddy. No, not everybody knows that the result of that integral is that. How did you get to that result? And well, we have to do some math there to do that. Some of the videos do explain how the integral is solved, but I think that practicing that won't hurt. So I want to talk about these three things. Today, I want to start talking about the first situation, which is a charged line. And I want to start setting up the problem. Let's see how much that takes or up to what point I get to. And depending on the time, I want to look at your electric field hockey solutions. If we don't get to do that today, then we'll see those on Monday. Okay, but I haven't seen the videos, by the way. I haven't seen what you guys turn in, but I want to see. I want you to show me what you did. We'll either do that today or Monday. Okay, so let's. There's Thor again. Somehow my bromance with Thor continues. So there that is. So let's talk first about this first situation, which is a charged line. What does this mean? Well, now we're not talking about a point charge. So we're not talking about one charge or that is located in a point that has no geometry. Now we're talking about a line. So it's a line that's charged. Let's assume that the charge is positive. Okay. The only thing that is common with the point charge is that the line is going to emanate an electrical field. Okay. So what is true here is that this this line is going to be emanating an electrical field. Why am I doing the arrows outwards? Can somebody tell me? Why are the arrows pointing outwards?
Because it's positive.
Because it's positive, correct, Andrea? If it were negative, I'd be pointing them inwards. For the purpose of the analysis, we're going to consider it's positive. The analysis basically gives us the expression we're going to get to applies both ways if it's either negative or positive. It's only going to be pointing in a different direction. But it's going to be emanating outwards because it's positive. However, if we were to be talking about a point charge, well, we know that emanation is going to be uniformly outwards because it's a point. But if it's a line, I want to know, or I would like to know, if I were to be located here in this point in space, what would the total electrical field be here in this point in space due to all of these lines that are going outwards? How are they going to interact in that point in space? And how can I represent the electrical field? We already have an expression or a formula for the for the point charge. And we know that for the point charge, the electrical field is K Q divided by R squared, or the distance. But what would the electrical field representation be for a line? Okay. Well, let's start analyzing that. Let me go to the next slide. Let's start analyzing that. Oh, whoops. My slides is hidden. Let's look at this situation and analyze what's happening here. Okay, I'm going to place myself here in this point in space. And I want to know what is the resultant electrical field in this point in space. Okay. Now, some of the things that we need to understand here that are important is that, first off, our line has a certain length. It has a certain length. Okay. Okay, the line has a certain length, so it's fixed. Now, what we're going to do is we're going to place a point here in space where I want to analyze the electrical field. Now, let's assume that that point generates a certain reference for us. Well, let's assume that we've got kind of like a free body diagram here for that point. And so I'm going to take that as a reference here. And I'm going to say that from that reference point, the distance from that reference point to the left is going to be called A. And the distance from that reference point to the right, I'm sorry, is going to be called B. And so L is going to be A plus B, which is a total length. But if I'm going to be taking a positive and a negative reference, the value of the distance to the left would be, if it's a Cartesian plane, would be minus A, and the distance over here to the right would be B. That's how I'm going to consider it. Okay. Now, there's one difference, an important difference between a point charge and the line charge. With the point charge, the point had a charge Q, and that was it. There was no geometry. So that charge that the point had was not distributed anywhere. It was just located there. Here, there's going to be an important difference in the sense that the charge, the total, the line is going to have a total charge Q. The total charge is going to be equal to Q, but that charge is going to be uniformly distributed along the line. Now, when we start having geometry, we start interpreting these distributions and we start giving them names. So that charge distribution, which is a linear charge distribution, is going to be represented by what we are going to be calling lambda. lambda is going to be the amount of charge we have divided by, in this case, the length of the line. Okay, so it's going to be newtons per meter, for example. I'm sorry, it's going to be coulombs per meter, for example. It's how the charge is distributed along the line. Okay, remember, if any of you guys have any questions, please let me know. Please stop me. We're gonna be doing this procedure in a very systematic way, and it's being recorded. But I do think it's important for you guys to follow along. Andrea, please go ahead.
I just have a question. What's the name of the symbol where it says A plus B?
Oh, that's just a fancy L.
Oh, okay. Like
I wanted to do an underscore L, but let me do this. So this would be
Thank
L.
you.
That's fine. So it's charge divided by length. Okay, charge divided by length. And so again, if the line is 2 meters long, and the total charge is 4 microcoulombs, okay, that means that lambda would be 2 microcoulombs per meter. Okay, that it's a uniform distribution of the charge along the line. Okay, by the way, this is a flat line. It's not assuming that the line has a width. We're going to be seeing those situations more in unit 2 when we talk about capacitance and plaques, but right now it's just a line. Okay, now how are we going to analyze this, or how are we going to analyze this situation? Because we want to see the combined effect of all of the line in that point P where I'm locating the free body diagram. And so here is where integral calculus comes along. What I'm going to do is the following. I'm going to grab a very, very small section of the line. A very small section of the line. Okay. That section is so small. That section is so small that I can consider it to be a point charge. It's so small that it's considered to be a point charge. Okay. And I'm going to consider that charge to be at a certain location along the line. That location is variable, and that location, I'm going to call it X. Okay. Therefore, this expression here is going to change. Lambda is now going to be the differential of charge, meaning how much charge is located in that point that I'm analyzing, divided by the differential of distance. How the length of that infinitesimal, very small space. And by the way, why am I using the same lambda? Because lambda is a constant. So if I analyze the 2 meters of length and the 4 microcoulomb charge, I'm going to get a lambda. But since it is a constant and it's uniformly distributed, if I focus on a very small section of the line, the relationship or the ratio is maintained. So if I'm looking at 4 microcoulombs divided into 2 meters, or I look at a very small portion of that, the proportion is going to be the same. The lambda is going to be the same. So this means that this this small section this small section here is going to have a certain charge. The small section is going to have a very small charge, and that's going to be that differential. So from here, we find that that differential of charge is going to be equal to lambda. I'm sorry, multiplied by the differential of the distance. Okay. So now I'm looking at a very small point that can be considered a point charge that has a charge that is going to be represented by lambda multiplied by the differential of x. Now, if I consider this to be a very, very small point charge here, then I'm going to forget about the whole line. I'm just going to be looking at that point charge. And so this turns in, or it's starting to turn into a problem that's very similar to the ones you guys already solved in the previous exercises. Let's forget about the line, and now I'm looking at just a small point charge here. And so if I do that, then that means that I'm going to have an electrical field, according to that point charge, that is going to be going this way. Okay. I'm going to call that electrical field. How can I call it? I'm going to call it EDQ. Okay. I'm going to be calling that EDQ. And there's going to be an angle here that I can actually calculate if I want. There's going to be an angle there. We okay up to this point? Now, what I want is I want to find the resultant electrical field regarding this point. So that is going to be, I'm sorry, I should have called this. I actually should have called this not EQ. I should have called it the differential. It's a part of the electrical field. The differential of EQ, of DQ. I don't like calling it DQ because it's too much D's there. I'm just gonna be calling it I'm gonna be just calling it well, yeah, that's fine, DQ. And that's going to be pointing that way. Now, I want the resultant electrical field. Now, notice what I'm going to be adding all of the differentials along this line. But notice something. Let's say that now I'm going to put myself over here on the other side at a distance that's exactly the same from here to here. This point here is also going to generate an electrical field. Let's assume that it's symmetrical. That's going to be pointing this way. And I'm going to call it this DE DQ2. Right? And it's going to have the same angle. Can somebody tell me what's going to be happening with those two electrical fields? And remember what we just saw in the previous problem. Anybody? What's going to happen with the X's and the Y's there? Anybody? Remember the problem number 4 that we were seeing.
I don't understand the question.
I'm going to say that again. Let's assume I'm located here like this were a point charge. Forget about the line. This is a point charge that's generating this electrical field, the one in pink. Okay. And I'm going to put myself on the other side at the same distance. And there's going to be this point charge here generating this electrical field here. what's going to happen with the X and Y components of these two? Without having to do any calculations, if these angles are the same, what's going to happen with these?
They're going to eliminate.
Which component is going to eliminate? And
The X.
correct. It's this situation. Remember in problem number 4, you have this and this with the same angle. So what happened with the X's? The X's cancel each other out because one is going left and the other is going right. And what happened to the Y's? What happened to the Y component in this situation? That's going to happen the same way.
Added.
They're added.
Yes.
Correct. They're actually duplicated. They're added. So this one would be this one was EA plus EB or negative if it's going downwards. And so what is the takeaway from this? Is that if I analyze the line and I start going point by point along the line, there's always going to be one point that's going to be equidistant from another point where the X components are going to cancel each other out. So actually, the electrical field that I'm going to be interested in, or the one that I want to analyze as a differential, is actually only going to be the sum, which Viviana said very well. It's going to be the sum of the Y components. And that means that the only thing I'm interested in is the Y component. And how do I calculate the Y component? It's going to be the differential, which is the pink one, multiplied by the sine of alpha. Okay. And so now let's do some, let's do some trigonometry here. If I look at the triangle that's formed here, I'm going to do a zoom on this triangle. This triangle looks like this. This triangle here. In that triangle, the distance is given by R between the point and the charge. The height is given by what I'm calling Z. And this distance over here on the bottom is called X. And this is the angle here. Can somebody tell me then what is the sine of alpha with regards to this triangle? What is the sine of alpha?
It will be 45.
We don't have any values, Estrella. We don't have any numerical values. With regards to these letters that are here, how is the sine of alpha represented?
Z over the hypotenuse.
Which I think Enya didn't, she was very kind because she could have said that she didn't understand my writing. This is an R. So yes, it would be Z divided by the hypotenuse, which is R. Okay, correct. And so let's substitute some things here. I know that if I consider this to be a point charge, then I know that D EDQ is going to be equal to K multiplied by DQ divided by R squared. But I know that this DQ, we already said that DQ is lambda dx. And oh, we're going to leave this like this, divided by r squared. So this means that going back to the original expression, dE, which is what I'm looking for, is k lambda z, well, I'm going to do this step by step, k lambda dx divided by r squared multiplied by z divided by r. And this is going to give me k lambda z dx divided by r to the 3. Okay. That's the differential of the electrical field according to this very small point that I am considering in the analysis. Okay. Now, why am I using differentials? I'm going to ask the question that all of you have in mind right now. Why am I doing all this? If I just found a mathematical expression for the differential, which is this red point here, which is a point charge, how can I find the electrical field for the whole line? What would I have to do? Let's remember your integral calculus. What would I have to do to find the electrical field of all of the line? If I already have an expression for for that point in the line, what would I have to do? Anybody? Remember integrals. I think that was last semester that you guys took integrals. What would I have to do with this expression to find the electrical field of the whole line? Anybody? Well, this is a little bit concerning. Okay. The purpose of integrals. Oh, okay. I'm going to go back a little bit because if you can't answer this question, then I'm really concerned. What does an integral represent? Anybody? What does an integral represent? Let's see. Jose Miguel, what does, and remember to turn on your cameras. What does an integral represent? When we're talking about integrals, what is an integral? Jose Miguel going once?
Yes. What does an integral mean? Did you ask?
Yes.
The inverse of a derivative.
That's correct.
That's the first thing I thought.
That's correct. It's the inverse of the derivative. That's the mathematical meaning of an integral. Correct. But what does it represent? So what is it useful for? That's another way of phrasing the question. What is it useful for? What does it do?
The area under a graph.
It's the area under the curve. But if I want to find the area under the curve, this is what you guys are taught that an integral is. I have a curve, and I want to find the area under this curve. And so what do? I grab a little, Jose Miguel, do you know right now what the area under this curve is? I hope the answer is no, because I don't. Okay.
No, sorry, I was muted.
But Jose Miguel, if I were to give you a rectangle, could you find the area of a rectangle? If I gave you this height and this value here, could you find the area of a rectangle?
Oh, yes.
Okay, so y is the function, and I'm going to use very little parts to define a series of rectangles here. To find areas of these very small rectangles. And if I have, Jose Miguel, 1, 2, 3, 4, 5, 6, 7 rectangles, what would the area of the curve be if I know the area of those 7 rectangles? I'm gonna rephrase the question if it wasn't understood.
Mm.
I have these rectangles and I can find the area of these rectangles. And I have 1, 2, 3, 4, 5, 6, 7 rectangles that I already have the values of their areas. What would then be the area of the whole curve? Anybody
That's
wanna?
maybe
Go
the
ahead.
sum of,
Yes,
I don't know, I'm not sure.
yes, yes.
Huh.
Don't look for complicated answers to simple questions. If it would be summing or adding these 7 rectangles, I'm sorry. That's what an integral is. An integral, what an integral does mathematically is that it adds very, very small things to get a total or a whole. Thank you. Thank you, Jose Miguel. And so I'm going to go back to the problem. I've already found here in green a mathematical expression that represents a very small part of the line that's considered to be a point charge and what the electrical field would be for this very small point of the line. If I want to find the electrical field of the whole line, what I'm going to have to do is that I'm going to have to integrate or sum or add all of the electrical field points along the line. Imagine that the line is comprised of an infinitesimal amount of point charges. So I know how to calculate the electrical field of a point charge. If the line is an infinitesimal amount of point charges, I have to add them all up. And that's what the integral does. Now, substituting the expression, this would be k lambda z dx divided by r to the 3. Now, r over here, r by Pythagoras is equal to the square root of x squared plus z squared. I'm going to also substitute that here. And this is going to be k lambda z dx divided by the square root of x squared plus z squared elevated to the 3. Okay. Now, can somebody tell me in that expression, in that integral, what elements of this integral here, which elements are constants? Meaning they're not variables, which is the opposing definition, meaning they're fixed values, they're constants, they're not variables. Can somebody tell me?
Okay.
Okay, correct. Thank you, Viviana. That's one of them. What is another constant?
You said lambda.
Lambda is constant, Viviana, correct. Because the charge is an amount and it's uniformly distributed. Lambda is only the representation of the charge with regards to the length. So lambda is a constant as well. What else is a constant? There's one more thing that's also constant. I'm Z. Z is a constant because I want the electrical field at a fixed distance. It's this height here, which is just because it might be blurred there. This distance is Z. Okay. This height here is Z. Those are constants. Can somebody tell me what is a variable, or what would be a variable in this in the expression?
That can have like different values.
That is that can have different values or is an unknown.
It would be
X.
X.
The X, and it's the X because this is the variable I'm using to generate the differential. So I'm locating myself at a certain distance, depending on the distance I'm at, is how the electrical field for that particular point is going to be. So X is a variable. And so this integral would be in the end represented like this. I'm gonna just give me a moment because I wrote this down too big. And I need everything to be on the same slide. So I just want to rewrite this so it's on the same slide. E is going to be the integral of dE. Oh, I'm gonna call this, by the way, E line. Just E line is going to be the integral of dE, which in turn is going to be the integral of K lambda Z dx divided by R to the 3. And this is going to be the integral of K lambda Z dx times the square root of x squared plus z squared elevated to the 3. And so if we bring everything out, EL is going to be K lambda Z times the integral of dx divided by the square root of x squared plus z squared elevated to the 3. Okay. Now, last question before you guys, last question before we start to wrap up. This, the way it's written, it's an open integral. It doesn't. It's just a mathematical representation. But remember that integrals have intervals. So I'm integrating from one point to another point. Okay, and that is going to give me a value in the end, a fixed value. I'm going from one point to the other. Usually integrals have those. Have those limits or reference. Can somebody tell me what would be the limits of this integral? It's going to go from where to where? And basically, remember, we're integrating along the line. What would be the two intervals here for the integral? Anybody? And look at the image. It's going from where to where?
Is it a
From-
number?
Well, we don't have any numbers here. We're only looking at what's on the image.
From A to B?
Yes, but there's just a little, correct, Andrea, but there's just a little bit of a detail. Since A is to the left, just as a reference, as a distance, it's going from minus A to B, from minus A to B, just because we're using that reference, okay, from minus A to B. And so I'm going to give you guys a task for Monday, and just because I'm a bit concerned about this, let me save this here. Okay. I think I'm good with you guys, giving you guys extra points. Okay, I give you a lot of extra points. But I'm gonna well, questions here before we I need to give you guys a task before we leave. Questions up to this point. Okay, let me stop sharing. Okay, everybody with your cameras on, please. Everybody with your cameras on. And we'll leave after this, okay? We'll leave after this. Boom, boom, boom. Okay, so you guys, for Monday, you guys have two things to do for Monday, or by Monday's class, okay? You have two things to do. The first one is I want you to rewatch, at some point, rewatch the video of the procedure done here to find that expression that we had on that we got to, which is that because we're not done with this problem yet, by the way. We're not done with this problem yet. Rewatch the video of today's session, okay? Rewatch the video. I mean, I know it's Friday right now and et cetera, et cetera. Rewatch the video, please, okay? And the second thing you guys need to do is, and this is for all of you, I want you guys to try to solve this integral. I want you to solve this integral here, the one that's on the bottom. I want you guys to try to solve this integral. Okay. Now, I'm generous with the extra points, but I'm going to do the following right now. And believe me, it's for your own good. It's not that I want to be bad or put you guys through grief, but I'm going to say it this way. Any engineer should be able to solve that integral. Okay. Now, I'm not saying that it's like Viviana could tell me, well, yeah, but anybody should be able to ride a bike. I don't know how to ride a bike, by the way. I don't know how to ride a bicycle. I'm not very proud of that, but I don't know how to ride a bicycle. And I would agree with Viviana, everybody should. I don't know how to ride a bicycle. I should, but I'm going to need to know how to ride a bicycle because of my daughter. So even if I don't know how to do it, I should be able to do it. If you guys are studying engineering and you already took integral calculus, you should be able to solve that integral. Okay. So by Monday, I need you guys to solve that integral. And I'm gonna randomly call upon one of you on Monday to explain the solution to that integral. Doesn't have to be a perfect explanation, but I expect an explanation. If the person I call upon isn't ready or doesn't show anything, everybody's getting 2 points deducted from next exam. And I'm going to call upon somebody else. If the second person up is ready, you guys are good. But if the second person up isn't ready, there's another 2 points deducted from next exam, and so on and so forth. Okay. I'm expecting the first person to be ready. Again, I don't expect a perfect explanation. You can go online. There's videos that explain how to do this, but you should be able to do it with what you saw in integral calculus. Okay. And on Monday, we're going to do that. Okay. If nobody attends class on Monday or something like that, because magically nobody logs into Zoom or nobody goes to the classroom, then everybody's going to get points deducted. You should, you should be able to solve that integral. Okay. Have it solved. Have it solved by Monday. Okay. There are people who didn't come to class today. Inform them about this situation because they are also subject to the situation. By the way, you can ask me questions during the weekend and I can give you tips. The solution isn't that complicated. It's a typical solution for a problem like that. By the way, I'm going to share something with you, and it's being recorded. I didn't remember how to solve that integral yesterday. I'm being frank with you guys. I was preparing class. I was like, I need to. I do some things with these classes. Remember when I taught you guys math? Always at the end of the semester, I rip apart my notes, because when I have to do them again, I want to remember. I want to do some mental push-ups and remember how to do things. And yesterday at night, that I was actually not feeling very well, I didn't remember how to do the integral. I had to go back to my notes and actually go online and remember how to do that integral. But I could do it because, again, I'm an engineer and I should be able to do it. So you guys are, your calculus course is much fresher than mine. I took it more than 20 years ago. You took it last semester, okay? So for Monday, let's have that integral solved, okay? You can have it written down and just show it on the screen and explain it. Or if somebody wants to walk us through the procedure, you can also do that as well. But again, I'm going to call upon somebody, and each person that doesn't know how to do this, we're going to have 2 points deducted from the whole group. Okay. And on the other hand, if whoever presents does a very good job, I'm going to give points to the whole group. Okay.
Can it be voluntary?
Yesel, you are developing. I am so proud of you right now. I'm extremely proud of what Yesel just did. That's what I call negotiation. That is what I call negotiation. Okay, so if somebody wants to volunteer, yeah, I'm going to allow that. I'm going to allow that if somebody wants to volunteer. That's good negotiation skills, Giselle. Giselle should get some Krispy Kreme donuts from the rest of the group, because she just kind of saved your butts right now. If somebody volunteers, you guys are free. So yeah, Giselle, good negotiation skills. I love negotiation. With me, negotiate. That was a good question, Giselle. Yes, somebody can volunteer. And if somebody volunteers and does it correctly, you guys are all free. Okay, good question, Jason. Okay, that's it for today. Any additional questions?
Yes, Professor, I wanted
ahead,
to
Tony.
know what was on with the extra credit for the electric field hockey.
Oh, we're gonna see those on Monday. I want to see your videos on Monday. We're gonna do that. I want to watch the videos, and everybody's gonna know who's gonna get the extra points and all that. Yeah, don't worry. We're gonna watch, because I haven't seen them, so I want to watch them, and I want everybody to see what everybody did. So we're gonna do that on Monday. Yep. Okay. Any additional questions? Estrella, go ahead.
Professor,
Mhm.
when is going to be the exam?
Oh, that's a good question as well. We're gonna set your dates. We're gonna do the exam on March 7th. March 7th. Okay, so you mark your calendars. That's a good question. I meant to mention that last class and I forgot. March 7th, and it's going to cover up to what we see next week. So you're going to have some, I think, next week. Yeah.
Okay.
Okay.
Thank you.
Okay. Good. See you guys on Monday. Have a good integral weekend. You guys are going to be bored this weekend. Now you have something to do. Okay. See you guys on Monday. Bye-bye. Have a good one.
Thank you.
Bye,
Thank you,
Professor.
Professor.